share a few announcements that I have first. And if you have questions on those, let me know, and then we'll jump into lecture. So first announcement, besides making sure your name on Zoom is your actual name, we have 2 assignments due tomorrow on mastering chemistry. So that is the intro to mastering and the primer. The chemistry primer, the purpose of it is just to get you familiar with chemistry language again, get you thinking along, some terms and vocabulary terms, so be it, that it's just going to be helpful in that regard. It actually, you don't get points deducted for wrong answers. It's kind of like if you do it, you get credit. So make sure you complete that. I have not checked enrollment on mastering yet, but I know as of Sunday, we were only like 50%. So please don't wait till tomorrow. Sometimes people run into issues where their access code isn't working for a certain reason. So if you run into that, I'll need to be able to help you. So all the more reason to jump on that, make sure that's all working today and get that done. We will have a quiz on Thursday. It'll be our first quiz. The format is this. It'll be on Blackboard. It'll be 5 multiple choice questions. It will be timed. I don't exactly know how much time I'm going to allot yet. It'll be 30 minutes or less. And it'll be open starting at 8 a.m. Thursday, and it'll be open till 5 p.m. So you have all day Thursday to get on at some point and complete that quiz. It will be over material that we covered last Thursday and today. It will not be over material that we cover in lecture this coming Thursday. Okay, so only material from our first 2 lectures will be on that quiz. You will need a calculator. If you have read my syllabus regarding quizzes and exams, I do not require the use of like the lockdown browser or the Respondus monitors, all that. So technically these are open note, open book, but you will be asked to sign an academic integrity statement that you will not use other resources. So other people, the internet, things like that. That is a cheapening of your own education if you choose to do that. And unfortunately, I mentioned that I have even online, even where people may have used the internet or things like that, I have spotted cases of academic integrity violations just from the spring. So please, you can use your notes and book, but please learn the material and use yourself for the exam. What kind of calculator do we need? Right now, just a basic one. You down the road will need a calculator that can do log functions. So it has a log button, but that's honestly not until we get to like chapter 10. So just a basic calculator for right now will get you through something you can add, subtract, something that can do exponents. Okay. We're going to get into scientific notation today and exponents. So a pretty basic calculator, not your phone. All right. So that is the quiz. Also check out the discussion board on Blackboard. I've gotten a lot of questions about, is this mandatory for a grade? It's not, but it's to your benefit. I tell people that I specifically am choosing the questions I'm putting and posing on the discussion board. They could show up again on a quiz or on an exam in a different format. So it is to your benefit to get on there and to participate. We've had some really great discussions so far from our first legit discussion board, not the meme one, but that one was fun too. And then also so for labs, we've had our group A and our group B. Group B people, I think it was clear from the email, you're doing the dry lab this week. If you look at that dry lab, it's a lot of work, and that's for a reason. This is going to be an excellent study guide for exam 1. So I want you to put in the work now to prepare yourself for that. But I'm also going to pick 3 or 4 questions from that dry lab, and I'm going to work them in like short 5-minute YouTube videos, and I'm going to post those so that you see if you ever get stuck on a question or how do I do this, you can watch those, and that should be a help to you. Also reach out to me via email. When is the dry lab due? It is due September the 4th by 11:59 p.m. so midnight. So that is a week from Friday. So you essentially have almost 2 weeks to get it done. The reason I did that is because you really aren't set to complete that dry lab until we finish a lecture on Thursday. Thursday, we're talking about density and specific heat and temperature conversion. So I kind of wanted to give y'all a week after that to get that done. So if you have completed the wet lab or you are completing the wet lab this week, feel free to also start on the dry lab at any point. You can begin that anytime. You can download it and start it on your own time. But all of that is due September the 4th. The wet lab people, Group A, you'll come do your lab this week, and your wet lab portion on Blackboard is due this Friday night. September or August 28th by midnight. Okay. That way you get it done and you're not piling up 2 labs in the same week and waiting and blah, blah, blah. So any other questions about labs or assignments that we have coming up? Chapter 1 homework is due less than a week now. It's next Monday at midnight. Okay. So keep an eye on that as well. That's on mastering as well. All right. That's all the assignments and announcements that I have. If you think of a question, just shoot me an email or type it in the chat and I'll try to check that as well. Okay, so we're going to get started with our lecture. So I'm going to share my screen. Also, did y'all find the polls helpful last Thursday? They were helpful to me. They gave me some good feedback. Unfortunately, I didn't actually type any polls for today, but I'm going to try to get some in for Thursday, but kind of wanted some feedback from y'all about how the polls went from you guys. So that's good to know. Okay, screen share. All right, you should be able to see my screen now. And I mentioned to you guys that I love to hike. We actually got out and did some hiking this weekend, but we kind of had to go early because, you know, it gets hot. We went out to Petit Jean and hiked the Cedar Creek Trail. That was really fun. I've done the Cedar Falls Trail, which is the kind of iconic waterfall trail at Petit Jean. But we did Cedar Creek, and that was a great hike. It went to this huge cave. It was about 4 miles. Really, really fun. You should check it out. But this is not a hike that is in Arkansas or even in our country. It is in Kenya. So I lived in Kenya for a summer back when I was in college. A fun fact, that's actually where me and my husband met. We both grew up in Arkansas, met in Kenya. Crazy how that happens. But I got to hike this inactive volcano, which is actually what it is. You could probably tell that. We got to hike around the rim of it. So we hiked up it and then we got to hike around the rim as well. And it was phenomenal. One of the most amazing experiences of a lifetime. So if you're ever in Kenya, I'm just kidding. It's near Nairobi, which is the capital of Kenya. And it just was, man, such an awesome, awesome hike. So that's my hike story for today. Measurements. That's what we're going to get into. We are going to talk about, just to give you a brief summary, we're going to talk about units and why they're important. We're going to talk about scientific notation, how to write numbers in scientific notation, manipulate them, and then we're going to get into prefixes. And we're going to use prefixes to start to work conversion problems, okay? And based on the stuff we cover in lecture today, you will need to use this stuff for the rest of the semester. So it's okay if you feel like I'm going a little too fast. We do want to kind of get through this material. But please know that these lectures are posted on Blackboard. They're all recorded. You can go back and watch them at your own pace, any point in time. Hopefully you found those in the lectures folder. I try to make those available at least by the next day. It takes time to process and upload to YouTube and all that. So they will for sure be available, if not tonight, by tomorrow. And anyways, so all that being said, let's start talking about measurements. Okay, with this slide, a measurement, what we're looking at is a physical quantity of something. So that's actually our first blank, a physical quantity. What is a physical quantity? It's a property that can be measured. Examples, we mentioned some of these last week, but mass would be one thing that we could measure. Length, volume, temperature, all those things are physical quantities that we can measure. And when we measure matter, we are determining a physical property that the matter has, okay? So we were talking about matter last week, how to classify it. There's all different kinds. We also talked about how matter changes, and it's helpful for us to measure the way it changes. So with a change, there's a starting point to the change and there's an ending point. And measurements tell us the starting point when we measure the beginning. And I didn't make a space for this, but the ending point as well, okay? Starting and ending point. So oftentimes you have to measure multiple times, repeatedly, throughout a change or before the change and after the change to learn what happened. Now, the most important statement on this slide is this last one. A physical quantity is described by both a number and, I'm going to put in all caps because it's important, a unit, okay? Units are critical. as you go about doing the dry lab, especially this week and next week, there's going to be times where you have to take a picture of a certain problem and upload it to the assignment on Blackboard so that I can see how you worked it. And if you have just random numbers with no units, I cannot give you full credit for that, even if you have the right numbers and the right answer, because units are essential. They're critical. And here's why. I'm going to make a point. If I tell you I'm 66, you have no idea what I mean unless I give you more info. I could mean that a lot of you might think age, okay? I could mean that I'm 66 years old. I know I look young for my age. I could mean that I am 66 feet tall, which I am not. And I could mean that I'm 66 pounds, okay? Unless I give you more information, technically the number 66 could mean any of those things or more, all right? All that to say, numbers are meaningless. Meaningless without units. So please, I'm begging you, people will do this, but please do not write a number on any problem without a unit next to it, okay? They all need to have units. Why else are units important? Not only do they tell us what we're measuring, they give us a reference point. I'm going to tell you a quick story to illustrate this second point, reference point. When I was in grad school, there were people from all over the world in my class. We entered grad school together. One of my best friends is from the Middle East. She's from Iran. And in the Middle East, they measure temperature in degrees Celsius. And here we commonly use Fahrenheit, okay? So, you know, if I ask her, hey, how's your family doing? You know, what's the weather like in Iran today? She could tell me, but I may not understand how hot or how cold that is unless I have a reference point. So from science, just the number of science classes I've taken, I've learned that about 20 to 21 degrees Celsius, that's about room temperature, okay? At home, my thermostat is set to about, you know, somewhere around 70 degrees Fahrenheit, a comfortable temperature. So 20 degrees Celsius is about equal to 70 degrees Fahrenheit. Now, if she tells me, oh, in Iran today, it's 50 degrees Celsius, then I can know, holy smokes, that's incredibly hot. Or if you're planning to go on a trip somewhere and you read a temperature or the weather forecast, you know, in Celsius, you don't know what it means unless you have a reference point, okay? So units are helpful for that reason. In the sciences, we use two systems of units, the metric system and then the SI system of units. Now, SI stands for the international system or the system of international units. Anybody have a thought on why it would be important for us to have a system of international units and not just all have our own metric units?
So there's like a common reference.
Mm-hmm. Yes, yes. I mean, because people do research, they do medicine all over the world, right? I guarantee you we're not the only country trying to come up with a vaccine for the coronavirus. Let's say another country beats us to it and they have their own system of, you know, quote, metric units. Well, if they can communicate those in SI units, then we can take that and redo or repeat their experiments. And that goes not just for, you know, a vaccine, that goes for any type of mathematics or medicine, you know, advancement in one corner of the world has been able to spread quickly because we have a system of international units. So they're critical. And this table is from your textbook, but it just shows you for whatever quantity we're talking about, mass, length, volume, it tells you the unit, the international unit and the metric unit. So you're going to have to be super familiar with metric units in this course. We're going to talk a whole lot today about the gram, the meter, and the liter. But just so you know, there's this international system as well, and the units can be different. You're gonna get real familiar with Kelvin as well. That's a unit of temperature. And then sometimes they're the same, okay? For length, same international and metric, they're both the meter, or for time, they're both the second, but oftentimes they're different. Okay, questions so far on units? Also, I will tell you guys, because I had a question about this from the first lecture, we're going to get into scientific notation here. So we're kind of switching gears. We're going to start doing some math problems. I'm not big on sig figs. We're not going to talk about rules for sig figs. I'm not going to request that you do a problem with a certain number of sig figs. So just know that. I do want you to do the problem correctly, and I want you to report the answer as accurately as you possibly can. But I just don't want you to lose sleep on an exam over, oh goodness, should I put 2 decimals or 3 decimals, okay? Don't sweat those things. So let's get into this. Scientific notation. What is it? Why is it useful? It is a way to make very small or very large numbers more manageable. We'll look at an example in just a little bit, but the general format is right here. And I know these are letters. I'm going to explain them. A times 10 with an exponent of B. So what does A and B mean? A is a number between 1 and 10. Okay, so A could not be 0.8. That's not a number between 1 and 10. A could be 8.3. Okay, any number between 1 and 10. There are decimals involved usually. B is the number of places that the decimal moved as you are converting a number from what we call standard notation. These numbers right here are in standard notation, and then we're going to convert them to scientific notation. We'll count the number of places the decimal moved, and we'll report that as the exponent. Okay, so let's do the first one, 83,910. We're going to write this in scientific notation. You don't see it right now, but if I were to write a decimal, don't convert it yet, just as a standard number, where should the decimal be for this standard number? Anybody?
Between the 8 and the 3.
That's if we convert it to scientific notation. As a standard, for us to know it's 83,000 and not 8.3, where's the decimal?
Oh,
After the 9.
Not after the 9. Good guesses.
before the 0.
The 3.
After the 0, right here. Okay.
Yeah.
Let me write it like this: 83910.0. That tells us, the decimal there tells us that it's 83,910. I'm trying to pull the chat up because I see there's some chat on there. Yes, after the 0. All right, so if the decimal is there, now we can count how many places the decimal needs to move or does move for us to turn it to scientific notation. So we want this to be 8. If we move the decimal all the way to here, between the 8 and the 3, now I have a number that is between 1 and 10, 8.3910. Okay, that's a number between 1 and 10. How many places did the decimal move? 1, 2, 3, 4 places. And it moved to the left. Okay, so when it moves to the left, the exponent increases. So times 10 to the, it's going to be a positive 4. And how do you know that? Well, check yourself. If I took my calculator out and multiply 8.3910 times 10 to the 4th, am I going to get 83,910? Yes, I am. So there's a rule here, and we're going to write that rule simply put. If the decimal moves left, the exponent increases. Notice that I didn't say the exponent is automatically positive. There may be times where you start out with -8 and then you end up with an exponent of -2. It increased there, but your exponent is still negative, okay? So if the decimal moves left, as in this case it did, the exponent increases. Let's look at the second number. We have 0.000596. So let's move the decimal until we have a number between 1 and 10. So where does the decimal need to be for us to get a number between 1 and 10?
5.96.
Yes, 5.96. So if I moved my decimal until it's after the 5, it moved 4 places, this time to the right. Okay. So now if it moved to the right, we're gonna have the opposite rule apply. So we should have times 10 to the -4 this time. So let's double check ourselves. If I take 5.96 and multiply it by 10 to the -4 in my calculator, will I get 0.000596? Yes, I will. So the rule here is if the decimal moves right, the exponent decreases. All right, we're going to do some more practice with this because all the decimal moving and stuff can sometimes seem confusing to people. So let's look at these numbers down here. I'm gonna leave the screen like that, so hopefully you can see all the rules and everything. But I'm gonna shut up for just a second. I want y'all to do the first 2 numbers. These are standard numbers, and I want you to convert them to scientific notation. And I really want to encourage you guys to be doing this with us. Okay, I definitely encourage you to get some paper out, grab a pencil, and actually do this problem with us. All right, so let's do these. So the decimal should be after the 2 initially. So for it to make a number between 1 and 10, I'm going to put the decimal between the 6 and the 5. So I should have 6.5932. So the decimal moved 1, 2, 3, 4 places to the left, which is exactly what happened on the slide up above. So we'll have times 10 to the positive 4. If anybody got anything different, let me know. That's what I got. But sometimes I mess up. Okay, let's look at the second number. I'm going to move the decimal until it's a number between 1 and 10. So it needs to be between the 8 and the 3. So that means the decimal moved 1, 2, 3, 4, 5, 6, 7 places to the right. So that means the exponent's going to be negative. So we should have 8.37 times 10 to the negative 7. Okay. Questions on that? All right, now you're going to find out the rules kind of flip when you are going from scientific notation back to standard, okay? And this, you could think of it, these number 3 and number 4 down here, think of them as just putting it exactly in your calculator. You're doing 7.41 times 10 to the power of 8. 10 to the power of 8 is a really, really, really big number. It's bigger than a million, okay? It's like 100 million. So if we multiply 7.41 times that, we are actually going to move the decimal 8 places to the right. Okay, so I'm going to do 7 and then 4, 1. So that's 2 places, and then I should have 6 zeros. And my decimal would be here. You can put a 0 there as a placeholder if you want. So now let's double check. Did I move it 8 places to the right? 1, 2, 3, 4, 5, 6, 7, 8. Yes, I did. And if you put this operation in your calculator, you should get that kind of number. You can check yourself that way. Okay, let's look at number 4. 3.021 times 10 to the negative 5. All right, so this is a really small number, so we're going to end up with a really small number. We're moving the decimal 5 places to the left. So if that's the case, here's my 3021, and I'm going to have 1, 2, 3, 4 zeros out front because the decimal was here, and it moved 1, 2, 3, 4, 5. Now the decimal is right there. So I should get 0.00003021. Questions on anything we've done so far? Okay, good deal. All right, so let's keep moving then. So now we're going to look at how to add or subtract numbers in scientific notation, okay? So we've got 7.4, addition and subtraction. Here's the rule. Exponents must be the same. So if you look at this first example right here, we see that we have 2 numbers, 7.41. The first number, that number has an exponent of 8. 4.32, we have an exponent of 10. So the exponents are different. So we're going to pick one. If you see how it's been worked out right below, we took this first number and we manipulated it so that the exponent matches. Okay, and what we did, we needed the exponent to go from 8 to 10. We needed the exponent to increase 2 places, or by 2, right? So remember, let's go look at our rules. We got to move the decimal to the left for the exponent to increase. So that's what they did. The decimal was here, and then they moved it 2 places to the left, and you get 0.0741. Now your exponent is times 10 to the 10. Now you can add these numbers together, and then you simply report your new exponent, okay? Or the exponent that matches. So that's how they did this first one. Let's work out this example on the bottom. Okay, so we have 3.021 times 10 to the negative 5 minus 2.86 times 10 to the minus 8. So our exponents are different. I'll tell you, it does not matter which one you pick. You could pick the first number or you could pick the second number. You just need to make the exponents match. So I'm just randomly going to pick one. We're going to pick the first number and we're going to make the exponents match. So what I need to do is I have an exponent of negative 5 and I want to make it negative 8. Okay. Now, when you think about negatives, which one's bigger, negative 5 or negative 8?
-5.
-5 is bigger, okay? So we're actually taking our exponent and we're going to decrease it to make it -8. We're going to decrease it 3 places. So if we are, for the exponent to decrease right here, we're going to move the decimal to the right 3 places. So I'm going to take this number down here, and I'm going to make it 3, 0, 2, 1, put the decimal there. It was between the 3 and the 0. I moved it 3 places to the right. Now I will have times 10 to the -8. So this is my new number. Okay, now I can subtract that from 2.86 times 10 to the -8. So you would put in your calculator 3021 minus 2.86. What do y'all get? You can type it in the chat. I got 3018.14. Is that what y'all got? And my exponent is times 10 to the -8. Now, I know some of you are thinking, but wait, you're supposed to have a number between 1 and 10. And yes, you are. So we're actually not done here. So it probably would have been easier had we picked the second number and converted it to have an exponent of -5, but we didn't do that. So we just have one more step. We're going to convert this, our answer here. It's not a number. This 3018.14 is not a number between 1 and 10. So we need to make it a number between 1 and 10. To do that, I am going to change colors really quick. We're going to move the decimal 1, 2, 3 places back to the left. So now we have 3.01814. And remember, if we move the decimal to the left, the exponent increases. So we moved it 3 places, so that should be times 10 to the -5. So that's our final answer. So we probably wouldn't have to have done that last little adjustment at the end if we would have picked 2.86 and adjusted its exponent to be -5, but we didn't know that at the time. We just picked one. So we fixed it at the end there. Any questions so far on adding and subtracting scientific notation? Numbers in scientific notation. Okay. We're going to move on then to multiplication. So multiplication. It's a little simpler. Multiplication and division are more simple. For multiplication, you just multiply your digits, kind of what I call your base number, and then you're going to add your exponents. So let's do that with this first one. So you're just going to have 7.41 times 4.32, and we should get a number. Anybody have that? You can type it in the chat or unmute yourself.
Is it 3.20112?
3.20. Did anybody get something different? You should get a number that's like around 30.
Oh.
7.41 times 4.32. I got 32.
Yeah, 32. I did the whole thing.
Oh, I see. You're a step ahead. 0.112. That's a lot of decimals, but there they are. Okay, we'll fix it to a number between 1 and 10 in the end. And then you're going to add the exponent. So this would be 8 plus 10. So you have times 10 to the power of 18. Now we're not done. We need to make this. Okay, I see in the chat. Good job, you guys. We're going to make this a number between 1 and 10. So I'm going to move the decimal 1 place to the left. Remember, when you move the decimal to the left, your exponent increases. So our final answer is 3.2 times, and then you could finish out all those decimals. I just didn't write them. Times 10 to the 19. Okay.
So if there are a bunch of numbers, would you want us to write them, or is it okay if we just do 3.2 like times 10 to the 19th? Or does it just
I mean, yeah, this would be an appropriate answer. Now, if it's a multiple choice, you know, I'm not going to give you choose between 3.2 times 10 to the 19 or 3.20112 times. I'm not going to do that to you. Okay, it's the same. So just give me a few decimal places. If it's a multiple choice, it should be obvious which one's correct. As long as here's where people get tripped up on these. They'll put an answer like this as their correct answer and not the finished answer. Okay, so make sure you finish it and you get a number between 1 and 10 as your base number. All right, one more example, then we'll do some division practice, and then we will move on to prefixes. Let's look at this one. So here we have we'll do 3.021 times 2.86. Somebody go ahead and type that in, shout the answer out, and then let's look at the exponents. We have -5. We're adding the exponents, so it'll be plus -8. So negative, and then the plus minus is a minus, so we have
Negative
-13. Yeah, that's gonna be our exponent. So what's our base number? Anybody get it?
8.64.
8.64, is that what y'all got? Okay, and then times 10 to the -13. Okay, now I know these exponents look really large. We have 19, -13, but when you multiply numbers with exponents, you get an even larger number. When you multiply numbers with negative exponents, you get an even smaller number. Okay. All right, division. What are the rules for division? So you divide the digits, subtract the exponent. So it's kind of opposite there. So you'll do 7.41 divided by 4.32. And here your exponent is 8 and 10. So for exponents, we're doing 8 minus 10. So what is our base number here?
So could we just write this one as like 1.76? Just round it up.
Yeah, that's okay to round.
Okay.
I actually haven't typed it in. 7.41 divided.
1.7152777778.
Yeah, don't give me 100 exponents. Just give me like 2 or 3. What is the answer?
1.76 is what I was gonna.
We'll go with that. And then 8 minus 10, we'll have times 10 to the -2. And we have a number between 1 and 10 here, so we don't have to do any other manipulation. All right, last one, and then that's it for scientific notation. So we have 3.021, and we're going to divide that by 2.86. Then we're going to subtract our exponents. So we have -5 minus a negative, oops. Yeah, that's good. -8. So negative ends up being -5 plus 8. That's a +3 on our exponent. So what's the base number?
1.06. Right. Yeah.
Anybody get something different? Y'all good? I see some thumbs up. Okay, good deal. All right, so we're going to move on. If you have any questions on scientific notation, this stuff will show up on the quiz and on the exam. So make sure you know the rules for multiplication and division and so on and so forth. All right, let's talk about prefixes. Prefixes, first off, just from the English language. What is a prefix? You guys should be familiar with this concept. It's a word that comes before a word, okay? So let's do a little scenario here. If I'm in a room with Michael Jordan and Jordan Sparks, and I just say, Jordan, you don't know if I'm talking to Michael Jordan or Jordan Sparks. What a fun room would that be, by the way? But if I put a prefix in front of those words, okay, if I say Mr. Jordan, now you know who I'm talking to, okay? The prefix denotes who I'm talking to. By the way, I have to pause here. Speaking of Michael Jordan, we don't really watch a lot of sports. We don't even have a TV. But I know there's a really popular Netflix documentary series, The Last Dance, about Michael Jordan that came out, and the Chicago Bulls, that my husband got super interested in watching it, like right when we had our son this summer. We had him June 7th. And y'all know newborns don't sleep very well. So the first week or two especially, I crash around 9 p.m. and I have to sleep. And he was super pumped about watching these documentary episodes. And he was like, hey, you go to sleep. I'll take our son and we're going to watch The Last Dance together. So I'm super thankful for that documentary, by the way, because it allowed me to get some sleep at night. But if I say Mrs. Jordan, now you know I'm talking to Jordan Sparks. And all that to say, prefixes, that's how they work. It's a word you put in front of another word that manipulates or changes the meaning of the word, okay? Or adds meaning, I should say. So just remember that. let's look at this. Scientists often deal with very small or large measurements, okay? For example, a virus particle is, guys, think about this, 0.0000, I'm still going, 0.00120 meters. Something that small is wrecking us globally right now, you guys. Oh, and then also on the other end of things, we have a very large number here. It is a lot of meters. This M here stands for meters to the sun. What is that, like 150 billion meters to the sun, okay? Or trillion maybe. So because these numbers have so many zeros, it's just hard, it starts to make your head spin, right? It's hard to actually comprehend how small is that. I know about how big a meter is, but I don't know how many meters that is. So using prefixes, we can make the numbers manageable. Also, y'all know I don't know how to spell very good, so if I misspell things, just laugh at me and move on. All right, so let's think about this. A virus particle is 120 nanometers. All right. Oh, I just gave away my question. I was going to say, does anybody know what NM stands for? N here is a letter that we put in front of M. I mentioned M stands for meters. When you put an N in front of that M, you'll learn, we'll introduce the prefixes in just a second. We now have a nanometer. Well, if a virus particle is 120 nanometers, that number one, just 120, we can grasp what 120 is. But you also have to grasp what a nanometer is, okay? So a nanometer is really, really, really small. If 120 of them are equal to this tiny amount of meters, okay? On the other hand, it is 150,000 capital M meters. Anybody have a guess on what that capital M stands for? It's a prefix.
Is it macro?
That's a good guess. It's mega
Yeah.
meters. All right. Or it's 150 million km. I bet y'all know what this one is. What does K stand for? Anybody? Oh, someone.
Kilo.
Megameters. Do what? Kilo.
Kilo.
Mhm. Kilometers or kilometers. So anyways, if we put a prefix, and here we're just abbreviating, but if we put a prefix in front of our unit and our measurement, now we have numbers that are more manageable. That's just the point. That's the purpose of prefixes. All right. So let's actually look at some prefixes and how they apply to different types of measurements. So if we're going to make a measurement, there's many different kinds we can make. We mentioned these on the very first slide, but the type of measurement is what I'm calling our base unit. So if I am measuring mass, I'm going to be measuring, the base unit is the gram. Okay, so your base unit could be a gram. If I'm measuring distance, my base unit is a meter. If I'm measuring volume, my base unit is a liter. Hey, I love that encouragement in the chat. Good job, Jayla. All right, so here's what you need to know. These three words we just wrote are going to be with us all semester long: gram, meter, and liter. If I say base unit, you should be able to recite those almost in your sleep: gram, meter, liter. All right. Gram for mass, meter for distance, liter for volume. And we're actually going to talk more about those today. So those are our base units. And the moment we add a prefix, we change the size of those. So these first three prefixes above this red line, you'll notice I've kind of divided this figure in half. The ones above the red line, these are larger than the base unit. All right. So a kilo. And y'all are actually more familiar with some of these than you think, okay? Kilo, we abbreviate K. If I tell you that I buy a car for $3K, what are you gonna say to me? Probably gonna say, you ain't going very far, because that's a cheap car. But you're gonna say, I spent $3,000 on the car, okay? So you know kilo is 1,000. So 1 kilo is 1,000 of your base unit. If it's dollars, a kilo, a K is $1,000. If it's grams, 1 kilogram is 1,000 grams. So the point here is that 1 kilo is 1,000 of whatever your base unit is. All right, hecto, you abbreviate with an H. 1 hecto is 100 base units. So which one's larger, a kilo or a hecto? You'll probably catch on. I have these listed by size. a kilo is the largest. It equals more of the base units. Okay, what about deca? Well, how many years are in a decade?
10.
10. Okay, so there are 10 base units in a deca. If we're talking about liters, a decaliter is 10 liters. If we're talking about meters, a decameter is 10 meters. Okay. All right, now the ones below the red line, these are smaller than the base unit. So let's look at the first one, deci. So because these are smaller, it's going to take multiple of these prefixes to get one base unit, if that makes sense. So 10, if we're talking about grams, 10 decigrams equals 1 gram, okay? Centi, there is 100 centiliters in a liter, 100 centimeters in a meter. And then also be taking note of the abbreviations as well. Milli. Milli is a very common one. Especially in medicine, we often measure things in milliliters and even microliters in research as well. There's 1,000 milli in one base unit, okay? Micro, there is 1,000,000 micros in a base unit. And notice I'm going to zoom in on the abbreviation here. It's kind of unique. It's a U, but it has this swoop on the front, okay? It's kind of tail on the front. So please don't leave that off when you're writing micro. Also, notice that milli is abbreviated with an M. And earlier I mentioned that M stands for meter, okay? They are both a lowercase m. So if you see MM, that is a millimeter. But if you just see a single M, that is a meter, okay? It's not a millimeter until you have two lowercase m's. All right, lastly, nano. A nano is a billion, so we got 10 to the 9. Nanos in one base unit. Okay, so nano is the smallest here, kilo is the largest. Questions on any of these? Also, I should mention, some of you may be familiar with prefixes and it was taught to you slightly differently. And that's okay. If you're like, I actually prefer to write it this way. Like some people would prefer to say 1 millimeter equals 0.001 meter, okay? Again, there's so many different ways these can be taught. So as long as the relationships are true, if you decide to work a problem using decimals like this, I'm not going to have anything against that. I'm going to also introduce these in scientific notation form. It's the same exact relationships we just wrote on the previous slide. We're just saving our hand here. We're just writing fewer zeros. Okay, so instead of saying 1 kilo is 1,000 base units, we just wrote 10 to the 3. All right, so this is perfectly valid to write it in scientific notation as well. Or if you want to use the decimal system up here, or if you want to write them like we did on this slide up here. There's multiple ways. All right, so that's a little bit on prefixes. We're going to get more into that, but I want you guys to have a tangible feel and grasp for how big some of these quantities are. So if I say, how much is a gram? You may not know, okay, unless you're around chemistry a lot. You don't know how much a gram weighs, how much matter that accounts for. You may be more familiar with a meter or a liter because you can go to the store and buy a 1 liter bottle of Coke. Okay, so you could get an image in your head of how much volume a liter is. But I want us to, that's what we're about to do, is get some tangible feelers for some of these sizes and physical quantities. So let's talk about length first. We're going to talk about length and then I forget what's after that, but it'll either be volume or mass. So length is a measurement of distance. And the base unit is the meter. All right. So 1 meter, the English comparison of that, the one we're more familiar with, is a yard. Okay, so if you watch football, you know about how big a yard is. If you have a yardstick at home, that's about a meter. Okay, so that's just kind of a tangible feel for how long, what distance a meter is. All right, what about a centimeter? Well, you'll notice we took a ruler here and we have measured in centimeters. If you hold your pinky up to that, a centimeter is about the width of your pinky. Okay. What about a millimeter? Well, same picture here. We've held a pencil tip up, and a millimeter is the distance between one of these two small tick marks. Okay, so if a centimeter is from here all the way to here, then a millimeter is just the distance between two of these. All right, so a millimeter is really small. It's about the width of your pencil lead. Width of your pencil lead. Any questions so far on what we're trying to do here, getting a tangible feel for these? This next slide, it's just a table that's actually found in your textbook. And the reason I'm showing you this is because, again, I'm asking you guys, you can use your textbook, you can use your notes. So this table will be very helpful for you as you go about working problems on quizzes and exams. I'm asking you to not have access to the internet. So you, by all means, can refer to this table for different relationships. It's got several different things. It's not just meters and micrometers or millimeters. It's also got yard, mile, foot and inches, and then how those relate to different metric prefixes, okay? So that's super helpful. That's in your textbook. Let's move on to mass. First off, mass and weight are different. A lot of people think they're similar, but they're different. Mass is the amount of matter in an object, okay? And that does not change. That's consistent. Weight is a measure of the gravitational pull on an object. So your weight would be different if you stood on the moon. It'd be about 1/6 of your weight on Earth, okay? Your weight can be different depending on where you're standing, but your mass is the same. If you stand on the moon or if you stand on planet Earth, your mass is the same. That does not change, okay? So the base unit for mass is the gram. All right, so how much does a gram weigh? Well, you can see from this picture here, we've actually weighed a dollar bill. And it's not exact, but it's pretty close, 1.015 grams. So we say a gram is about the weight of a dollar bill, and we all deal with that. So we know how much a dollar weighs, not very much. So $1 bill, okay? Now, what about a kilogram? Okay, a kilo is 1,000 grams. How much does a kilogram weigh? It weighs about the mass of a loaf of bread. Now, I have put the best bread up here, guys. I don't know if you've had Killer Dave's. It's kind of expensive, all right? But you guys are health professionals, so y'all need to spend money on what matters for your body. Look at this. 21 whole grains. Look at that. Omega-3s. You got 5 grams protein. I'm not even kidding you. I could eat a piece of this bread by itself first. I don't even care if it's the heel of the bread. I would eat it. It's so good, okay? You don't believe me? Go try it. But I would encourage you to buy it from Sam's. Just find somebody who has a Sam's account and be like, hey, can I borrow your card? Because, you know, Sam's is expensive too. But it's the best bread out there. So anyways, a kilogram is about the weight of a loaf of bread. All right, this table right here is other relationships as well, but specific to units of mass. And again, it doesn't just have our metric prefixes and stuff, although it does have that. It also has pounds, it has ounces. So that's really, those are really helpful equivalents as well. And that's in your textbook too. All right, lastly, we're going to talk about volume, and then we're going to start doing some simple conversion problems. Okay. All right, volume is the measurement of the space occupied by an object. The base unit is the liter. Now, pause really quick. I put this picture on here. Right here, we use, and you probably recognize this if you've had a science class or something in high school with a lab. This is a volumetric instrument. Okay, it's this one in particular is a graduated cylinder. We say graduated because all these markings are called graduations. And we may not actually get to do this since we're not in lab very much in person this semester, but I just want to make sure that you know how to read these before you leave this course. Liquid, when you pour it into a volumetric instrument, it curves, okay? So we have this nice curve here. And I want to ask you, where do we read how much liquid it is? Do we come over here and where it curves upward? Do we read it right here? Do we come down to the bottom of the curve? Do we read it there? And if, again, in the middle, yes, we read it right here at the dip, and that is called the meniscus, okay? That is how you read volumes in volumetric instruments. All right, moving on though. If we have a liter, what is the English comparison? It is the quart. Okay. Now I could have put a quart of oil because you commonly buy oil for your car in a quart, but that's way less fun than pints of ice cream. 2 pints, for those of you who are in the kitchen a lot, 2 pints is a quart, okay? This happens to be my favorite ice cream. We don't even have a storefront though in Arkansas. You have to go to like Tennessee if you want to buy it at the store. Now there are some like bougie grocery stores that sell this because it's kind of expensive, but it's so worth it. Jenny's ice cream is seriously the best. She's like the queen of ice cream, y'all. If y'all watch that video, I have her cookbooks. I make her ice cream, but I've modified it a little bit. So anyways, her ice cream is seriously the best. So go to like Whole Foods. I don't know if Trader Joe's has it. Anybody been to Trader Joe's? Any Trader Joe's fans out there? I can't see y'all, so I'm just gonna pretend there are. All right, but 2 pints is a quart, and a quart is the English comparison to a liter. Let's look at the next one though, a milliliter. A milliliter, what's the volume of that? Well, it is about the size of your pencil eraser. I know they're holding their pinky up here too, and you could say, oh, it's the tip of your pinky, but everyone's pinky is a little different, right? So I like using pencil eraser. And this is just your standard ACT pencil here. Okay. Lastly, there's one relationship I want to point out with volume that I want you to memorize. It's right here. We can measure volume 2 ways. You can measure it with your metric units, which is like your liter, milliliter, microliter, or you can measure it in what we call cubic distances, C-U-B-I-C, cubic distances. Okay, and we will use cubic distances for things that are have a very regular shape. For example, a cube. Okay, it's got a nice shape to it. You could easily whip out a ruler, measure the length, the width, the height, and get the volume from looking at those measurements and multiplying those together. You have the space occupied in 3 dimensions. Okay, so if we have a cube here, we see that it measures a centimeter on each side. So we would call that a 1 cubic centimeter cube. All right. Now, what you need to know, the relationship between cubic distances and then your metric units is that 1 milliliter equals 1 cubic centimeter. Okay, 1 milliliter equals 1 cubic centimeter. You are going to need that. That is going to be consistent all throughout this course as we talk about density a whole lot, some on Thursday. That relationship is going to be critical. Okay, there's going to be times where you have to convert from metric units like milliliter to cubic centimeters and so on and so forth. So just know that's the same. This next slide, I'm not going to talk about a whole lot. This just gives you additional relationships between those metric units of liters or deciliters or centimeters, or sorry, deciliters or milliliters and their cubic distances, okay? So you could see here 1 liter and then the equivalents in cubic distances, all right? But the one I want you to know is the one we circled, and here it is again over here, 1 cubic centimeter equals 1 milliliter, all right? So that's just a visual for those of you who want more info on that. But lastly, this table is for volume, units of volume. This again is in your textbook, and this just gives you several great relationships between those metric units and then other units such as gallon, quart, fluid ounces. So make use of that as you work problems as well. Now, here's an important slide. Which prefixes are so common that I'm not going to give them to you? I'm going to have you either look them up or memorize them. I would encourage you to memorize them so that you can move quickly on a quiz or an exam, especially since those things are going to be timed, which are so common they won't be given to you. I'm not asking you to memorize all these, but here's the ones I want you to know. Kilo is very common. You need to know that. Centi, and then the 2 below it, centi, milli, and micro. Okay, so when I say I want you to memorize it, here's what I want you to memorize. The prefix and its relationship to the base unit. Okay, the prefix and its relationship to the base unit. So how many grams is in a kilogram? Okay, or you could phrase it the opposite way. How many kilograms are in a gram? And then same concept for centi, milli, and micro. How many micro, whatever, liters, grams, or meters are in a gram, a meter, or a liter? All right. So know those 4. All right. So that gets us to simple conversions. take a water break. So again, make sure you have your calculator handy. We're going to spend the rest of our lecture time working some simple conversions, okay? So let's see here. We're going to get rolling on this, but look at one thing real quick. Okay, simple conversions. Now, before I get started with this, you're actually very familiar with doing conversions, but just for common things. I'm going to give you an example. If I were to ask you to go to the store and buy 144 eggs, they don't sell eggs as individual eggs at the store, right? They sell them mostly by the dozen, okay? I know they sell them in different size cartons as well, but the main one is by the dozen. So if you're going to bring back 144 eggs and you can only buy them in the dozen, you need to know how many dozens is 144 eggs. So if you know the relationship that 1 dozen equals 12 eggs, this is a relationship, okay? You can convert individual units of eggs to dozens, right? And then you figure out, okay, 144 eggs, that's 12 dozens. I'm going to go buy 12 cartons of eggs. You just did a simple conversion factor in your head. You didn't hardly even need pen and paper, right? So we're going to now use conversion factors to obtain an equivalent quantity in a different unit. And that's just what we did with the eggs and the dozens. At first, I was talking to you in terms of eggs, and you took that info and you converted it to dozens, okay? It's a different unit. You have units of individual eggs. You have units of dozens. Now, what is a conversion factor? It's just a relationship between, I'm going to abbreviate, 2 units. The relationship between 2 units, okay? All right, so I have some questions posed on the right side of the screen, and we're going to look at a few of these. I may actually not do every single one for time's sake, but we're going to do some of them. Let's read this first question. It says, I have 1.36 kilograms, and the question is, how many grams is that? 1.36 kilograms is how many grams? So I need to convert from units of kilograms to units of grams. So I need the conversion factor. I need the relationship between kilograms and grams, and it's actually written right here for you. You could also get it from those slides early up in the lecture where we introduced prefixes. Now, you can write it like this, the one I boxed in, but an actual factor, and I'm going to encourage you to write them as factors, is where you have a numerator and a denominator. So you can write it 2 different ways. This relationship that we boxed in can be written with kilograms on bottom, which is this first one, or kilograms on top. And it all means the same thing. You're relating these 2 units together. And we know 1,000 grams is in a kilogram. So to work this problem now, I'm going to start with the number given, 1.36 kilograms, all right? And then I'm going to multiply it by the conversion factor that is going to allow me to cancel kilograms, okay? So look at, I'm either going to pick this one or I'm going to pick this one. Which one will allow me to cancel kilograms? If I'm going to write my conversion factor on the top and bottom of this line, and if I drew a line right here, you can see that I already have kilograms on top. Everything, if you write a number by itself, it starts out with that unit being on top, unless I were to write it like this, 1 over 1.36 kg, which I have not, okay? We've not done that. So right now, our unit of kilograms is on top, and I need to cancel it. So which one should I pick?
The one with the kilograms on the bottom.
Yes, so 1 kg. I'm going to write 1,000 grams is the equivalent. So things that are equivalent go directly on top and bottom of each other. So there's my conversion factor. Now I'm going to cross out kilograms. I have it on top and bottom, and in the world of mathematics, when you have things and chemistry, top and bottom, they cancel. So the only unit I have left is grams. And one more important thing, when I write my answer, if I'm going to, the question's asking for grams, I need to make sure that unit is in the numerator. And is it? Yes, it is. Grams is in the numerator here. So now we just do the math. 1.36 times 1,000, and I get 1,360 grams. Okay. Questions on that? So that is what we call a simple conversion. For the exam, and we'll get to these on Thursday, we're going to work up to what we call complex conversions. Okay.
Would it
And those
matter
might
if
include
you-
4, 5, or 6 steps. Yes, Taylor.
Would it matter if you use 10 to the third instead of 1,000 if you write it down?
That's
Like-
perfectly okay. So she's saying, what if we do this? Like that, Taylor?
Yes.
Yep, you can do that.
Okay.
10 to the 3 and 1,000, same thing. Okay. So again, if you want to, and that's especially helpful. I often do that when I'm dealing with micro, because micro, there's a million micros. So I'll just write 10 to the 6 instead of a million. Okay.
Okay.
Some people may, well, no, I'm not going to, you write it however it works. Okay. Just make sure the relationship is accurate as you write it. All right, let's look at, I'm going to skip over the middle one. Let's go down to the third one, okay? Because I want to get to some other problems before time is up. So we have 1.23 liters, and the question is how many milliliters? So how many milliliters is in 1.23 liters? And we can see over on the left side of the screen, here's the relationship. 1 liter is 1,000 milliliters. And then it's actually already been written as conversion factors for you with liters on the top or the bottom. And we'll pick which one we're going to use in just a second. So I'm going to write 1.23 liters, and I'm going to multiply it by my conversion factor. And I want liters to cancel because right now I have liters on top. And I want to make sure that I end up with milliliters on top. So it looks like I need to pick this second one right here. I'm going to write 1 liter. And then you can write 1,000 milliliters, or you can write 10 to the power of 3 milliliters on top. And we see that liters cancel out. So now we just do the math. 1.23 times 1,000 is 1230, and my unit is milliliters, okay? Sometimes people will get confused and they'll invert these conversion factors, and they'll write, you know, they would use the wrong one, and then you would end up with milliliters on bottom, and then your units of liters would not even cancel. So you just double check that your units cancel, the ones you need to cancel, and that you end up with the correct units that you need in the numerator. Okay. All right. Let's look at this first one down here on the next slide. So I'm going to give you guys a second. I want you to go ahead and start trying to work it. And then I'm going to jump in. I'm going to give you maybe 20-second head start. And I'm going to jump in and we're going to work this first one. Read it and start thinking about what relationships you need. Turn this sideways so I have more space. Okay, we have 36,589. What is mg? Anybody know?
Milligrams?
Milligrams, okay? And it says is how many kg? Kilograms, okay? Here's my question. Do we have a relationship that lets us know how many milligrams is in a kilogram?
Yes.
We have relationships for milligrams and grams and kilograms and grams. So I know that if I look up at the I don't want to like make y'all's head spin, but if you look up at the tables we worked on earlier, you'll see this: 1,000 milligrams, I'm just going to abbreviate, is equal to 1 gram. And then we also wrote this: 1 kilogram is equal to 1,000 grams. And you can write 10 to the power of 3 for those, no problem. But I don't have a relationship just yet that is directly from milligrams to kilograms. All right. You can write one out. Okay. So how would we do that? If there is 1,000 milligrams in 1 gram and 1,000 grams in 1 kilogram, you would have to do 1,000 times 1,000 to get how many milligrams is in a kilogram. Okay. And so that would be what? 1 million. Right? Or 1,000 times 1,000. Yeah, 6 zeros. Okay, so there is 1 million milligrams in 1 kilogram. Okay. Now, if this is confusing to you, you don't have to work the problem with this. You can work it just fine with conversion factor 1 and conversion factor number 2 that we just wrote out for those relationships. And let's do that. So I'm going to start with the number given, which is 3,658.9 milligrams. And I want to use the conversion factor, either number 1 or number 2, that's going to let me cancel out milligrams, because my answer should be in units of kilograms. So I need to cancel milligrams. All right, so I'm going to pick this first one, and I'm going to write it as a factor, a numerator and a denominator, so that milligrams cancel. So I'm going to draw my line here, and I'm going to write 1,000 milligrams on bottom, 1 gram on top. All right, so now milligrams is going to cancel, but we're not done. We don't have units of kilograms yet. We have grams on top. That's it. So we got to keep going. So we need to use the next factor, which relates grams to kilograms. Okay, so now I'm going to write 1,000 grams on bottom because I already have grams on top. I want grams to cancel. So I'm going to write grams on bottom here. That equals 1 kg or kilogram. And we have grams on top, we have grams on bottom. Anytime that happens where you have it on top once and on bottom, you cancel those out. And all we have left, the only unit we have left is kilograms. Is it in the numerator? Yes, it is. So that's good. Now we just do some math here. We have 36,589 divided by 1,000. Okay, so I know there's a multiplication sign right here, but because our number is on the bottom of this line, we're actually dividing by 1,000. Okay, and again, I know we're multiplying by this conversion factor, but we're multiplying by 1 over 1,000. So you just divide by 1,000 2 times. So essentially, you're dividing this number by 1,000 twice or by a million. So what you should get is that right? 1, 2, 3, 4, 5. Is that what y'all got?
Yes.
You get 0.036589. And what's my unit? Kilograms. Okay. Questions on that?
Is it okay if we round, or do you want us to write all of these out? All of this one out?
I mean, I'm okay if you round, but don't round like crazy. Don't be like, oh, it's 0.0. Well, you'd have to say 4. That would be a lot of rounding. Give me some decimals, okay?
You want us to put it in scientific notation?
I won't count this wrong if you did this on an exam and like for time's sake, you just moved on. I won't count that wrong. But scientific notation is fine as well. So how would we actually write that in scientific notation? Let's do that really quick because I think we can. We're going to make it a number between 1 and 10. So we move the decimal 2 places to the right. So we get 3.6589 times 10 to the negative 2. Either answer is appropriate. Great question. Yes, reading the chat. Okay, so that's what we just did. All right. Here is microliters. Let me see if there's a different one I want to work. Let's do this one down here, nanograms to micrograms. Now I know I'm skipping over a few. I definitely encourage you to like work these problems that I'm skipping over. But for time's sake, we're gonna work one more and then we'll about be done with our allotted time for lecture today. So we'll probably come back and work some more of these on Thursday, but you can see there's also more that I'm not even getting to. And we'll try to pick up and move forward and work those on Thursday as well. But please, in your meantime, work the problems that I skipped over to kind of check yourself of how well you understand what we talked about today. So here's the question. We're doing this one right here. We have 578,965 nanograms. We want to know how many micrograms is that. And remember, micrograms is abbreviated like this. It's the U with the tail on the front, okay? So if we're going to convert from nanograms to micrograms, if we were to flip back to the prefixes slide where we wrote out all the relationships, again, we don't have a relationship that directly tells us how many nanograms is in a microgram. But we do know this, we know how many nanograms is in 1 gram, because a nano is smaller. In fact, it's the smallest. Does anybody remember how many nanograms would be in a gram?
1 billion.
A billion, 10 to the power of 9. Okay, we also have a relationship for how many micrograms is in a gram. Anybody remember that?
1 million.
Yes, 10 to the 6. So you could handle this problem perfectly well by using these 2 conversion factors, okay? And we'll write them as factors when we actually work the problem. But if you want to do it in one step, we could get a conversion factor that goes directly from nanograms to micrograms. And you do that by looking at these numbers here and figuring out what the difference is. If there is a billion nanograms in a gram and 1 million micrograms in a gram, the difference here is 1,000, okay? The difference is 10 to the power of 3. So what that means, nanograms is the smaller prefix of the 2. That means there is 1,000 nanograms in 1 microgram, okay? We looked at the difference between the 2 numbers as they relate to the base unit, the gram. And then we just wrote a relationship for these 2 prefixes, which are both smaller than a gram, okay? So I'm going to work it using the 2-step process, and then we'll see how it was shorter and quicker with the 1-step process. So let me erase this. So start with the number given, which is right here, 578,965 nanograms. We're going to multiply it. First, we're going to convert to grams. So we're going to use relationship number 1 right here. And I want to write it as a factor, numerator, denominator, so that nanograms cancel. Right now I have nanograms on top. You could pretend this is over a 1 if you want to write it like that, if that helps you. So I'm going to write 10 to the power of 9 nanograms on bottom, 1 gram on top. Now we see we have nanograms on top and bottom, so those are going to cancel. And I'm left with grams, but we don't want to stop there because the question says how many micrograms, not grams, so we got to keep going. So now I'm going to use relationship number 2 that we wrote out down here, and I want to cancel grams. So I'm going to write 1 gram on bottom, 10 to the power of 6 micrograms on top. Now we have grams on top here and on bottom, so those cancel. And then we could get our answer. Everything cancels except for micrograms, and is the unit that I want on top in a numerator? Yes, it is. Micrograms is on top. So you would take 578,965, divide it by a billion, 10 to the power 9, multiply it by a million. Remember, numbers that are on the bottom, the billion right here, you divide by that, and then you multiply by 10 to the power of 6. You multiply by a million. So what you should get is 578.965. I'm too close to the edge. And the units there are micrograms. Is that what you guys got?
Yes.
Okay, great. Now, if we work it real quick, we have 1 minute left. If we started out 578,965 nanograms, I'm going to kind of speed through this, and we use this bottom conversion factor. Here's it's 1 step simpler now. We're going to write 10 to the 3 nanograms on bottom, 1 microgram on top. Nanograms cancel because I have them on top and bottom, and we're left with micro. We just skipped over the grams part. So we just see we divide by 1,000, and you should get the same answer. And that's the unit that did not cancel. It's in the top, so that's nice. Okay. You can also put this in scientific notation as well, and I would accept either answer, standard or scientific notation. But that's it for today. So again, you have the quiz coming up. I'll send emails about that, but that's it for lecture day. Does anybody have questions? I will stick around for 3, 4, 5 minutes and answer questions if you have questions, but if not, you are free to go. Thank you for joining us, and we'll see you on Thursday.
I have a question.
Yes, Dallas.
So like for my textbook, I still won't get my textbook until the end of the week through the bookstore. Was there like a link that you had to access the textbook in the meantime, or?
I mean, does anybody that has purchased the Mastering Chemistry, did you get access to the electronic textbook
So
through that?
if you're in Blackboard and you go to the mastering stuff, if you scroll a little down, there's one that says access to my ebook or something like that. It's not like a book, it's just like a virtual one.
Okay.
Yes,
I
the
haven't bought my
electronic
textbook because of financial aid, and it gave me a free 14-day trial, so I can do my homework and everything and still get like the points for that until
Yeah.
I can buy my textbook.
Because their books have been like on back order or something like that, so I don't
My
know.
goodness, yeah. I'm not allowed to comment. Is what I'm but the e-text is available. It should be available for you. Again, it's kind of like a giant PDF, but it's organized. You can click through the different chapters, and it's the same information. It's the same material. It's just going to be on your computer screen or whatever.
Okay.
So if you want to read through things in the textbook that way, you have access to that. But again, too, a lot of this information is, some of the figures and things, not exact, but a lot of it's on these lecture slides. So if you just want to refer to the lecture slides as you go by, that should be helpful too.
Okay. All right.
Yep.
Peace out.
Okay. Any other questions?
Yes, I have a question.
Okay. Who is Caitlin or Kaylin?
Yes. I was wondering how you got, so I see 10 to the power of 9 and then 10 to the power of 6 from the nanograms to micrograms. Is it the reason why in the end it's 10 to the power of 3 because you're going to a lower, metric system?
So prefix, I think is the word you mean.
Prefix, yeah.
Yeah. So the nanogram is the prefix that when you put it in front of the word gram, a nanogram is the smallest one that we've talked about in this class so far. So a nanogram is smaller than a microgram. It takes a billion nanograms to get 1 gram. Well, it only takes a million micrograms to get 1 gram. Okay. And so because of that relationship, the difference here is that if we're just looking at how many nanograms is in 1 microgram, based on those differences, 10 to the power of 9 divided by 10 to the power, or the difference there between 10 to the power of 6 is 1,000. Okay, so there would be 1,000 nanograms to get 1 microgram, and nanogram is the smaller one, so that's why it takes more of those to get 1 microgram. Does that make sense?
Yes, thank you.
Mm-hmm.
I think I missed the part where I was distracted, but did you say for the tables that you gave us, like the conversion tables, that we could or couldn't use them on quizzes? I know you had us.
Quizzes are open note, so.
And then we're supposed to memorize those 4 that you told us, just to make it easier so we wouldn't have to go back and look.
I would, because if not, you're gonna have to go look them up every time.
All right, okay.
And that's gonna take a lot of time. And let me tell you, there's moments you're probably gonna feel pressed for time on an exam. And so I just say memorize them, get them down, know them. That way they're second nature to you, and you're not worrying about finding information in an already stressful moment,
Right. Okay. Just
Yep.
thank you.
But yeah, they're open note. So, and lecture slides are totally considered notes. Any other questions? These are all great questions. Okay. Well, if you do have a question, shoot me an email. I will be sending out probably a class-wide email maybe this evening, maybe tomorrow. So keep your eye for that. And I will see you guys in lecture on Thursday. All right. Y'all take care.